Right, so today our objective, we're going to finish the other side of the intakes first. So that'll take roughly like 10 to 15 minutes. So we'll get started. So first we want to make a part. So right chain, and then we can start the drawing where we want it to be. So on this surface, because we're putting it on these sprockets. So that's what we want to do. And then you click Start 2D Sketch and click the correct plane that we want to draw on. So this one. Okay, and then we remember that we have to do project geometry and construction lines to get the centers of these two circles. So we can just do that. And then with these geometries established, we can draw directly on the CAD using those center points. And then we're basically trying to draw the chain path right now. So we need some sort of like kinda elliptical shape. So we're going to need two tangent lines across here. Notice how they're not tangent right now. That's because we're going to make them tangent by using the tangent tool here. So that's why it doesn't matter where you put the lines initially. And then finally you trim off these ends. So you just click on trim and trim these off. Alright, then you want to add a work point, right? So we can start one right here. Actually, no, I don't like that. We're going to start one right here. Right, and then we're going to pattern this around the chain. So we click on this point, click on this, and then select curve length, which is the length of the curve, and you divide it by 0.386, which is the length of each individual chain. And then we click these two radio buttons and apply. And we see that our work point gets patterned nicely across the whole entire chain. And then we're going to turn the sketch back on because we're going to need it later. Alright, so with that done, we can first CAD the padded tank treads, which are these things, these links with pads on them. Not the flaps, we're going to do that right after. So, okay, so we're going to remember where our point was. Which is about somewhere here, okay. And now we want to bring in a padded tank tread. So, chain and tank tread traction link. They're also called traction links because they have pads on the surface that grip surfaces really well. And this is exactly what we need. We need to make a plane here so we have like a surface to constrain everything to, or all the chain links to rather. And we're going to use this plane right now. So if we go into the part in the bottom left here, we can click on origin and choose the XY plane and constrain it to the work plane we just made so that it's nice and in line. Right, hello. And then we're going to have to constrain this padded link to our first point. So we're going to click on, oh wait, these are the old links, my bad, okay. We're actually going to use a link from the new library. I used my old library. So we're going to use library 1.2 because they have something counted for us that's useful. So if we go here, you find the exact same things. They have this little orange thing going through the middle, which is like important for our second constraint. So I'm just going to redo the first constraint. Boom. And then we need this axis, and we need to constrain it to the first point that we made here. And then you click apply, and then your chain link's kind of like this. We need one more constraint. We need to align it with the chain path. So you click the XZ plane and the chain path, and then you set it to either 90 or negative 90. You're going to have to try both. And if it's wrong, like this one, you just switch it to the other one. So you can edit the constraint down here, and boom. And if everything's done properly, it should pattern itself nicely around the whole chain once you click on pattern components and you click on the feature pattern. I'm going a bit fast because it's covered last week and we have some other things to cover today as well. So yeah, and then we need to find the path which we made in right padded chain, and boom, if we click it, you see how it patterns itself really nicely around. This is exactly how you would do it in real life as well. So if you're building this in real life, this is how your rollers would look. And now let's get rid of all these sketches with all those numbers and all that stuff so it'll look nicer. So yeah, that's the padded stuff. Now, what about these flaps? We're going to have to add those in somehow. So let's do that right now. So in principle, it's literally the exact same process, except notice how they're all spaced out a little bit more. So that means we have to like specify some different numbers, but all in all, it's pretty much the same. All right, so we're going to name this right flap path, I guess, and do exactly what we just did before with a small twist. So we go to the surface we want, start 2D sketch, and find the correct plane. All right. So now we're going to do the same thing. So project geometry, construction lines, and we're going to find the center points of both sprockets. And then turn off construction lines so we can draw in our circles. The circles are roughly just like the size of the teeth, or like goes right between here. So you can really just guesstimate that. If you're guessing a bit too big or too small, it really doesn't matter, because in Inventor, chain is probably like 50% aesthetics, other 50% function. So like personally, when I make CADs, that's why I do chain at the very last. So my renders will look realistic and pretty. But if I'm gauging like clearances, I don't need chain to do that because the sprockets already tell me that. So this is why we do this at the end. Now we have the path sketched out. We just use the point. We're gonna start it where we started it before. So here. And then we're going to pattern it around. So this is the only difference, essentially, between what we did like 5 minutes ago and what we're doing now. So we click on the point, we click on the direction and curve length, and this is the only difference. We're going to make the spacing, we're not going to divide this by 0.36, but 2 instead, because we want it to be spaced further apart, because these are the flaps, not the padded treads. That's the only difference, and we can apply that. And now we have to bring in the padded tank tread. No, sorry, the flaps. There's 3 types of flaps that come with effects. You can choose which one you want to use depending on what you're using it for. There's like short flaps, medium flaps, and tall flaps. It depends on your application. On this robot, you probably want to run medium flaps because the larger the flaps are, the more reach in the front, right? Because these are further out, they can reach the cubes better. So if they're not perfectly aligned, they have more tolerance, which is really good in driving and programming because it's more tolerant of error. So we're going to choose medium flaps. You see the short flaps are a lot shorter, tall flaps are a lot bigger. The reason why we typically don't run tall flaps is the more friction surface you have, the more strain you put on these motors. And if you typically when you have like tall flaps, that means you likely stall your intakes out, which is never a good thing. Okay, so if you recall, the last thing we did here was we had to make a work plane. That just basically gauges the center of the sprocket there. And then we're ready to constrain this flap. So, right, we constrain the, okay. We need to choose the right plane. I believe it's the XY plane. Right, and then we constrain to here. Notice how it's off-center because for some reason the designers of these parts in CAD made it all the way up here instead of to the center. But it's okay, we can get around that by just applying offset here. And I find that 1/2 inch works nicely, so boom. And then we're going to have to constrain the second constraint, which is the axis here, so this thing. And then we have to constrain it onto the first point we drew. That's actually important. If you don't constrain to the first point you drew, bad things could happen. This is actually kind of hard to access because we already constrained a layer on it, but I'm pretty sure it's this point. Oh, click the wrong thing. Okay, we need to find that flap again. Is that the right point? No. Okay, that's the right point, and then we have to find the first point we drew, first work point, which is It's not letting me hover over it because I'm using the wrong constraint. So this one, and then apply, and then you see it puts itself here. And now we just have to apply the final constraint, which is the angle constraint. We constrain its whatever this plane is with this, and we want it to be at 90 degrees, right? And then we choose this, boom, and you see it's in the right direction, so we don't need to flip it to -90. So now we have one link done. We use the path we made to pattern it around. So we click on the thing we want to pattern just like before, go into modeling here and go to the rectangular pattern we made. And you can see when I click it, it patterns itself nicely around the intakes, which is really cool and really satisfying. And with that done, we just turn off the helpers that we made. So the sketch in the plane, so it looks nice. And that's our intakes done. And yes, this is exactly how they would look in real life. And these intakes are, I guess 2 ways to call them are like, they're meta intakes. Meta means like the design most people are going after, like 90% of the teams. A word of advice for if you guys are competing in Vex next year, like when you're designing your own robots and competing and all that, don't, like, crazy ideas are called crazy for a reason. Like, typically, especially your first year, you want to build something that's meta, which is like what everyone's doing. Well, you might be worrying, oh, it's not unique, it's not going to look good to the judges, whatever. But typically, things that are meta for a reason. They're simple, they're reliable, and they're probably the most efficient concepts. So if you find yourself building a robot that's really similar to other teams or whatever, although it's not the best feeling, but there's nothing wrong with building something similar. But don't just flat out copy them. That's pretty bad. That's like that. Then the robotics loses its point, right? You're doing robotics to learn and like because you're interested in it, not to like copy other robots. What I'm trying to say is sticking to the design everyone else is doing is perfectly fine, and that's certainly a mistake that I made in the past, which I still regret last season. But yeah, Inventor is loading. After a few seconds, it should respond again. Oh god. Did my Inventor crash? Yeah, that's why you save your work periodically. Thank god it didn't crash. Okay. So we're gonna save this immediately. It's taking a while to load. Also, on a side note, if you guys have opened Inventor recently, you might have errors, like saying like it can't find your license, or I don't know, like there's an error and it's reporting to Autodesk. What you do, Inventor actually had an update, which is like 2020.1 or something. You just want to update it to that, and you'll be fine. And you also want to update the licensing service, so you would find that in the Autodesk desktop app. You can just search it up on your computer and like the type here to search bar, and you should be fine. Alright, so there we have it. Nice. Okay, so the robot is technically functionally complete. There's one small detail that I would like to add. One issue that a lot of teams have, especially early season, is you see how there's like a big gap between the intake flaps and here. So, and then you might be wondering what stops the cubes from like being misaligned here. Like you can, let me just show this to you. So if we take away this cube, a common issue that happened that flagged a lot of teams was this. Boom. Boom. Alright, so since there's like nothing guarding the cubes here, what stops the cubes from, while being intake, to be misaligned like this and consequently jam against here, right? So you want to build some sort of guard that kind of guides it in this empty space here. And that's really easy to do. Most teams just attach it to the intakes, which we're going to be doing right here. I want these cubes back. I guess not. Alright. Right, if it doesn't want to give me my cubes back, I'll just constrain it myself. So that's just really going to need 2 small pieces of plastic. I guess that's a good refresher for making custom pieces in Inventor, which is really half the purpose why Inventor is here, not only in Vex but real life, so you can make nice custom components. We don't have 3D printers, and that's not legal in Vex, but This is why we use CAD software. But that being said, there's still ways to manufacture your own custom press without 3D printers or laser cutters that we've done before. We'll probably cover that in like a later meeting. We're talking about like advanced build quality or something. Okay, we're just going to put these cubes back. And we're going to put on the 2 small plastic pieces. So you see, like when we add like chain constraints, for example, these are really complicated constraints. Like when you start adding them, you're like you might find that Inventor starts becoming really slow because these are like really complicated constraints. So that's why you always want to do these constraints near the end. I'm not going to add another cube because I don't want to make this more complicated than it needs to, I guess. So we'll add it at the very end. All right, so going with our idea, we're going to add small plastic tabs here. Another issue is like when there's no cubes here and the cubes in the tray are free falling down, it might get misaligned here as well in the intake. So it might be like diagonally shifted. To prevent that, we can use like the guards here as well. So you'll see in a moment. It gets pretty intuitive. Okay, so how should we do this? Okay, so I guess I'll draw what I mean. So basically we have our intakes here, right? So we have our intakes. So this is like the metal C channel here. So this thing. We want some sort of guard in this area, right? So what a team called 7K did, they basically had a piece of plastic that went like, let me make this thicker. They basically had a nice piece of plastic that went like this. If I remember correctly, something like this. And then, yeah, piece of plastic kind of bent like this. So that means the tubes will be guided up straight upwards. And when you're spinning the intakes outwards, the cubes would autocorrect against the smooth surface here as well, which is really nice. So that's the type of thing that I'm trying to do here. To actually sketch this is actually quite tricky. Okay, to sketch this is going to be quite tricky. We can do it one way. Yeah, well, let's do it this way. So instead of using plastic, I'm going to use aluminum bars. At that point, I think it's just a matter of preference, but in Inventor is easier. So that's what we'll do. I'm going to save it again so I won't lose my work. All right, so we're going to rob a spacer here. Actually, no, these spacers are better. All right, so this part is actually really simple to build, so that's nice, and the robot's almost done. Maybe we'll mount the brain as well if we have time at the end. The brain is basically the central processing unit of the whole robot. It's where you upload your code and tell the robot what to do, and it's directly connected to the lithium battery, which powers the whole robot. You might be wondering, lithium batteries, can't you make like bombs out of those? The answer is yes, but please don't. So that's that. Alright, so we're probably gonna need like 7 hole, 8 hole long, so let's grab 8 holes. Alright. I believe I showed you guys how to bend parts in our flywheel video, so I'm gonna run through this kind of quickly here as well. If you guys want like a refresher, just look up our flywheel shooting mechanism video. We bent a piece of metal there, like a plate. Here we're bending bars, but it's literally the exact same thing. Oh god. It's lagging again. Okay, I'm gonna restart Inventor. Give me 2 seconds. It's usually not this bad. I have a feeling it's because I layer chain on top of chain on the intakes. So typically you do them right before you render, but in this case we just have like a few more things to add. Alright. Alright, we're back. Nice. I just remembered something. But first we're going to return to where we just were. Return to where we left off. So this is exactly why you save your work. If we didn't save, oh boy. That's unlucky. So we just really need to put these 4 spacers back on. Because the chain added so much complexity, I'm thinking about not mounting the brain. I'm just trying to keep this assembly as simple as possible in case you guys want a copy of it, so it doesn't die on your computer. Alright, so we're going to put this here. Alright, so now we're going to grab our bars again. So again, we want it in kind of like here. I actually think 10s might work better, so we'll use 10s. Okay, here's like an important note, so make sure you know this while you're CADing. Once you go here, vex plate, since, oh, it doesn't even give 10s. Okay, we'll use 9s then. Okay, so when we're making, because we're bending one part like, let me draw this. Because we're bending one part like this and the other part like this, whenever you know that whenever you modify one part, like as long as all the parts are the same, it'll modify that part as well. So if we use the same piece of like same part in the Inventor library, if we bend one, the second one will automatically be like this. And if we bend the other one back, it'll turn into like this. We want them to be different. What this means is we're going to have to make a copy here. So, and it's perfectly fine to do this in your libraries, by the way, because you're the only one using them. So we go like this. You see how we have a 1x9 plate copy? These are going to be 2 separate parts now. So that's really nice. That means we can bend them in 2 different ways. And we can just smack them on here. Okay, goddammit. Inventor doesn't let you rotate when you have a lot of parts. So we're going to use free move up here. It's usually not this glitchy. Right, free move. Talking about glitching, especially when you're just starting to CAD, you might have a lot of sick assemblies, like sick up here assemblies. You want to make sure your CAD rig doesn't have any of those, because what that does, one bad constraint will ruin everything. Like one bad constraint will ruin all constraints down the road. So you really want to make sure all your constraints are good and you don't have this button, like you don't have that button active. Just make sure about that. It's a matter of habit. It's going to be tedious at first. It might mean that a CAD that you worked really hard on for like a month, you might have to restart because you had broken assemblies. That's just life. And then once you get used to it, you can really just CAD like I am right now. So there's definitely a learning curve. Right, now we're gonna have to bend this metal. One is longer than the other. That's very interesting. I thought they were both 9s. Oh, because my perspective is whack. No, one is longer. Oh, because the C channels are not symmetrical. That's very interesting. Right, so this C channel seems to be 1 hole longer. Alright, that's pretty... Never noticed that, but that's okay. We're just gonna shift all this down then. You might be wondering in real life if the C channels are not perfectly even, like this is slightly longer than this, would it matter? If everything clears, like the doctrine here is like if it works, right? If it works, then you can keep it, probably no big deal. But if you like really want your stuff to be even and like have aesthetic value, like you're more of like what do you call it? Form over function, I guess. More of a form over function person, then keeping it even will be a lot better aesthetically. Personally, I try to keep all my things even because it just bothers me to look at this, but it's okay. This is CAD, so. Alright, now we have to bend these. Pretty simple. You double click on the part, start 2D sketch here, and we just have to draw the bend line. We're going to bend it about here, so no. We're going to bend it about here. So you can literally just draw an arbitrary line here. And since I want this to be consistent on both sides, I'm going to make a dimension. And throw in some random value. And then we click on bend part, which is down here, bend part. You click on the bending line and Inventor does all the dirty work for you. So like this, that's a bit too much, so we want to change this. It's in radians. I don't remember why it's in radians, but that's not a big issue. It looks like I have to put in the exact units. Okay. That looks a lot better, so we're just gonna keep this. I'm gonna save this for the other side. Alright, so this is kind of the idea that I was talking about. And you can notice how since the two bars are different parts, this bar is not affected. So now we just simply do this to this part. Start 2D sketch. Okay, I remember I did it on the third hole. Or like the fourth hole. I think I did it on the fourth hole then. Right, so did I start a 2D sketch? Yes, I did. Okay, so if you want to go back and edit a sketch, or I'm just gonna make a new one. Can't find it. It's totally fine. And we need to draw a line, so boom. And to ensure consistency on both sides, we're gonna make this 0.064 as well. Well, why did I choose that number? Well, it's arbitrary, but it also happens to be the thickness of metal and the max and like the thickness of Lexan that or custom plastic that you can buy. So it's a handy number to have in your head. Alright, you can see how like this part is not guarded and the gap between here and here is greatly minimized. I think that looks pretty good, so I'm gonna save. Nice, okay. Right, okay, you know why it's offset? Because this is constrained like this and this is constrained like this. Let's just fix this right now. It's literally takes 2 seconds. And after that, I think we can basically call it. And next week is going to be rendering, which is going to be a lot of fun. Rendering, depending on your computer, might take like overnight, for example, or maybe just like an hour or two. It really depends on your CPU. Like Inventor really likes CPU. Like Inventor's performance depends on your CPU mainly. So depending on your CPU's performance, renders can take like from again 1 hour to like overnight. Typically I like to do my renders overnight because maximum quality and I'm not using the computer for anything else. Unless it's like before a test or something. So overnight is usually pretty nice. And yeah, there's also different types of ways you can render. You can ray trace, which basically I forget the exact point of ray tracing, but it essentially like it makes the lighting look a lot better, I'm pretty sure. And you also have like normal rendering by iteration, and it's just a different way of rendering. And ultimately, just choose which one floats your boat. For me, I like ray tracing, but it's not a huge difference. The motor is mounted one hole down as well. Okay, it's pretty easy to fix. Why do we use small washers here? Because like the inserts on like the 12-2 or like the square inserts, they're made of metal. And if you look at the C channels, they're made of metal as well. And when you have metal rubbing against metal, as you can like kind of imagine, it's a lot of friction. This is why we like to use washers between two metal and metal surfaces. Yeah, that's no problem. See ya, have a good day. Alright, so now we just smack the motor back on. So this will probably take like 5 more minutes since people have to go eat dinner and whatnot. So we're almost finished. Okay, motor goes here. Wrong way. Nah, I did the constraint wrong. Okay. This is probably the final piece we need to put down. So, and we're not putting the brain and the battery on the robot because one, it's pretty obvious where they go at the back of the robot and you have a lot of mounting space for it. So the necessity to CAD it is really quite minimal, but maybe I'll do it like after the meeting or something. We'll see. It makes the robot look more realistic anyway. And yeah. And two, because adding the flaps, like these chain assemblies, really increase the complexity of the model, and we had an Inventor crashing us once already, so we don't want that happening again. Okay, we're gonna save. I guess we have a few more minutes, so I'm just gonna show you guys what the brain and the battery is. The brain, the battery, and all your V5 electronics is the heart of every robot. So if you go into electronics, the V5 brain is this. So now, like after like Turning Point, which is like the 2018-2019 game, we are all blessed with a new VEX control system, which has touchscreen, has nice V5 ports similar to Lego EV3, and it's just like a lot better than the previous system where you had like spaghetti cables and it was just a huge mess. You guys are very lucky to have this system. This system is quite good. In the early days, the ports really like to die. Now it seems a lot better, so that's fine. That's the brain, nice touchscreen with like 21 V5 ports. This is a battery, lithium ion, I think, so pretty juicy. Yeah, don't do anything bad to it or else it will do bad things back, like overheat and blow up. So yeah, and where will we mount these on a robot? You see how like when we like fold in, we just really can't. We just need to make sure this red area isn't taken up. So this is like the edge of this wheel represents the furthest boundary where you can mount all your parts. So you can either mount your brain or the robot brain rather. Oh god, I click on the part. Whenever you click on a part and drag it, that's not supposed to be dragged. Inventor is really unhappy. You can either mount your brain like here, horizontally, or here vertically. Just mount it in an area which is not going to get hit when other robots start ramming into you. Battery, similarly, I would mount it on this brace right here, so it's really accessible. Right. I can actually do that right now. It's going to take 2 minutes. So to mount the battery, you want battery clips. 2 of these, and then you want 1/2-inch spacers. These things. This takes 2 seconds to do, so in real life and in CAD, so I'm just going to do it. It takes 2 seconds to do unless you have no more space left. So typically when you're building, please don't leave this to the last moment. Like, it's like kind of like filling up a bucket with rocks. You always want to put the bigger rocks in first, and you put the little rocks in after. Same idea comes to building. You always want to make sure all your big parts clear, and then worry about the smaller parts. Like, by big parts, I mean like physically in size and in complexity and importance. So intakes are a top priority, for example, in Tower Takeover and in Change Up especially. And it applies in various other seasons as well. Okay, now we just have to angle it 90 degrees. or rather 0 degrees. Yeah. Or the other way to do this is like this. So we're going to do this. And hopefully it'll cooperate, and no, it doesn't. Okay, I'm gonna angle constrain it first. So I have a feeling it's because the surfaces on the battery aren't exactly straight. So we're just gonna do this first. After we mount this battery, I think it's good enough for today. So battery mounted at 90 degrees. Okay, that's not what 90 degrees looks like. We can just fix that really easily. 0, boom. Oh, it's angled really whack. Okay, that means this surface isn't perfectly horizontal. Okay, then the easy way to do this is this. So when you drag the part in, because we grounded our assembly directly in line with all these axes, you can just rotate the part until it's correctly oriented, and then you just use the mate constraint and mate it onto here. And also, by the way, you're only allowed to have one battery on your robot. There's no way you can run 2 batteries with one brain anyways, but just keep that in mind. Only one set of V5 electronics for a robot. And that's how you would mount the battery. And yes, we have space for it, so it's super easy. Alright, so this is the robot. 9 cubes capacity, because one more cube would fit down here. If you want to have more, you can build an extension thing, or like an extension that we showed in a previous video. Against like the L18s, for example, is a really good example. That's like if you wanted like 10 to 11 cubes. If you just took this robot, and I'm just gonna stop the recording now.